Hello, my name is Phys2212 and this is my Physics 2 Lab 1 on charged tapes. This is going to give us hands-on experience with electrostatics, and we're taking it to the Python model to see how accurate it actually was. Purposes for this lab, the big question was, when does the electric force between two charged objects become strong enough to actually counteract gravity? To answer this, we suspended two pieces of tape above each other and measure the distance at which one floated above the other, and compared that with predictions from our Python code. Our main findings of the floating distance was about 1 centimeter, and the downward gravitational force was about 0.00196 newtons. And charge need for tape was about 4.67 nanocoulombs. It's a very small amount of charge, but it's enough to cancel the tape's weight. The principles we use here are Coulomb's law, which says that electrical force between two objects depends on how big the charges are, which is the Q at the top. The constant K is huge, which is about 9 billion, which is why even tiny charges can create like noticeable forces. Gravity, on the other hand, is really simple. It's F equals mg, and because the tape is so light, its weight is only about 2,000ths of a newton. So these things kind of go well together, and that's why the tape floats. You see our free body diagram on the right; they bounce each other out. Our system consists of the two U-shaped tapes. The surroundings includes the air and the supports like the chairs and our hands. For assumptions, we treat each tape like a point charge at its center, like geometrically. And even though in reality the charge is spread along the length, we assume that the charges were evenly distributed, and we ignored air resistance or tiny air currents. So our initial values were 0.2 meters, 2 times 10 to the negative fourth, and 0.00196 newtons. So pyramid setup here, you can see our chairs and the tape. We just hover the piece of tape underneath the other one to make them float. When the two tapes were brought together, they repelled, which told us they had the same signs, like they were both negative, they're both positive. And when we held them near a neutral object, like a pen, they attracted because the tape induces a dipole in the neutral object, and so it attracts. So we saw it with a pen and with a table. This simple setup gave us measurable data about a very abstract concept, like the charges are super small, and like sometimes you wouldn't even notice this stuff if you weren't looking for it. But this tape is super light, so it makes it easy to see. That's our force balance calculation here. At equilibrium, the upward electrostatic force equals that weight, so we plugged it into Coulomb's law. We put in our numbers, constant K, our distance of 1 centimeter, and our force. The result was a charge of about 0.67 times 10 to the negative 9th coulombs per tape. So that's in a billionth of a coulomb, but it's definitely still enough to make the tape float, which is why we saw the results in our experiment. Here's our coding implementation. So we built it in Python. We created two spheres to represent the tapes and arrows to show the forces of gravity and electric field. And then let the program calculate the charge needed for balance. So we just set them opposite each other and it said like balance it out basically. And the constants we used matched our experimental setup. G, K, and the mass the same, and the distance. And the code gave us the exact same result as our hand calculation, which is pretty crazy. It also estimated that this corresponds roughly to 2.9 times 10 to the 10th missing electrons, which really shows how even losing a tiny fraction of electrons creates noticeable forces. Jesus. Sorry about that. This is our data versus model here. At 1 centimeter gap, the electric and gravitational forces were equal. But of course, the model simplified and some additions come in, treating the tape as a point charge. The charge leaking away, obviously, from like humidity or like us touching it by accident. And the fact that we estimated the tape's mass or density value, which might not be exactly. These limitations don't change the overall conclusion, but they help explain like why like in real world like it doesn't happen every time. Like, we had to do the experiment like quite a few times to get it to actually work, whereas the model works every time, and that's why. Start two what if and why questions here. First is what if the electrons were positive and protons were negative. In that case, all of our observations would look the same because attraction or repulsion depend only on opposite versus same charges, not which particle carries which. So it'd be exactly the same, just the labels are just swapped. Second, why do we handle the tapes as little as possible? The reason is that our hands and other objects provide a path for charges to escape. If the tape discharges, the electric force decreases and the tape won't float. That's why minimizing contact is essential. So like, every time you touch it or like anything hits the tape, you're losing like tons of electrons, which makes a huge difference. The key takeaways here is that our floating gap is 1 centimeter. We went over all the data, right? But small amounts of charge can balance the weight of light objects, and this lab really highlights how powerful electrostatic forces are. It's a super small amount of charge you can see there. Can counteract gravity on like a lightweight object, and I think it's a really like nice first lab. Thank you.